Today's lesson is going to be on 7.5, the heat of combustion and heat of formation. Our learning target for this section is I can calculate enthalpy changes for various chemical reactions. The first thing that we're going to look at is what is known as standard enthalpy of combustion. Standard enthalpy of combustion is going to be an enthalpy change. So how much does the enthalpy change when 1 mole of a substance burns or combines with oxygen? So this could also be combusts, because that's what combining with oxygen means under standard state conditions. Another way that we talk about this, another way that it might be referenced, is heat of combustion. Standard state conditions is something else that is important for you to know. So our standard state conditions are going to be 25 degrees Celsius and 1 atm or 101.3 kPa or 760 millimeters of mercury. This is otherwise known as our standard state conditions. Okay. So we have an example here. We've got C2H5OH liquid plus 3 oxygen gas becomes 2 carbon dioxide plus 3 H2O liquid. Our enthalpy here is negative 1366.8 kilojoules. Now, if we were talking about this in reference to C2H5OH, our enthalpy of combustion would be this exactly, because there's only 1 mole of C2H5OH in here. So because there's just 1 mole, this is our enthalpy of combustion for C2H5OH. Enthalpy combustion often is going to be in reference to things that are known as hydrocarbons. So hydrocarbons are going to be compounds that are composed of only carbon and hydrogen. Some will also have oxygen, and they have large enthalpies of combustion and are usually going to be used as fuels. The reason that they're going to be used as fuels and having large enthalpies of combustion is because they have lots and lots of intermolecular forces in them, which when those intermolecular forces are broken, when we are combusting or burning, we're going to have a big release of heat. And remember, releasing of heat is going to be negative, which is why all of these values are negative. So if we're looking at our substances over here to the left, our substances are going to be the very first thing. So if we're referencing carbon, so we're looking at carbon here. When we were talking about this carbon, hydrogen with the hydrogen here, magnesium with magnesium here, sulfur, carbon monoxide. And then our bottom ones, these guys are classified as, these bottom few down here, these guys are going to be classified as our hydrocarbons. So our hydrocarbons are going to be kind of, some examples would be these guys down here. And you can see that the numbers increase greatly. So up here we've got like negative 393.5. Down here we've got negative 890. So down towards the bottom, that's going to be our hydrocarbons, our hydrocarbon compounds. So that's going to be stuff like methane, acetylene, ethanol, methanol, and isooctane. Those would all be different hydrocarbon-based fuels. So we're going to go ahead and kind of look into an example problem of what we would be doing with heat of combustion problems. So it wants us to determine the approximate amount of heat produced by burning 692 grams of gasoline, which is C8H18. We want to assume that the enthalpy of combustion of gasoline is the same as isooctane, which is a common component of gasoline. So we've got our moles of gasoline, or our grams of gasoline. The first thing that we want to do is determine our moles. So step 1, we want to make sure that we know how to convert to moles. So I'm going to kind of write step 1 down here. We want to make sure we have our amount of moles. So obtain moles. That's step 1. So we're going to obtain our moles. And remember, moles is equal to mass over molar mass. So just as a reminder, how we find molar mass, we look up each individual element on the periodic table and we multiply it times its subscript and then add our numbers together. So we've got 8 times 12.01, which is our molar mass of carbon, plus 18 times 1.01, which is our molar mass of hydrogen. When I add those up, I end up getting 114.26 grams per mole. All right. So we've got our molar mass. The next thing that we want to do is calculate our moles. So we're going to take the mass that was given to us, 692, over our molar mass, which we just calculated. So our moles is going to be 692 over 114.26. And this ends up giving us roughly 6.06 moles of C8H18. So we've got our moles of our substance. I'm just going to box this in orange just so we can visually see it very well. Okay, so there's our moles. Now what we want to do is we want to take our moles, and we're going to take our moles and we're going to multiply our moles times our enthalpy of combustion, which is delta HC. Now it told us that we're going to be using the enthalpy of combustion from isooctane. So we find isooctane up here, C8H18. It tells you that the enthalpy of combustion for that is negative 5,461. It's telling you its unit is kilojoules per mole. So, and the unit for this, kJ per mole. This is going to end up giving you kilojoules, or heat released. So we're going to take our moles, which is 6.06 moles. And we're going to multiply that times our enthalpy of combustion, which is negative 5,461 kilojoule per mole. At this step, the unit moles can cancel out, so we're able to get rid of moles, and we're left with kilojoules, which is our unit of heat, which is what our question asked for. So 6.06 times negative 5,461 gives us negative 33093.8. Our unit is kilojoules. All right, so remember our steps. Figure out your moles, take your moles, and multiply times enthalpy of combustion. So, looking at this practice problem, I want to know how much heat, so I want you to solve for kilojoules. So we're going to solve for kilojoules. Is produced by the combustion of 125 grams of acetylene. Acetylene is on your list up here. It is C2H2. So I'm going to go ahead and pause the video and give you guys time to work this one out, and you're going to record your response in the question. Okay. So next, for this one, we're going to take our 125 grams of acetylene and divide by the molar mass of acetylene, which ends up being 26.04. And that ends up giving us 4.8 moles. We're going to take our 4.8 moles and we're going to multiply it times the enthalpy of combustion for acetylene, which ends up being negative 1,301.1. And that unit, remember, is kilojoules per mole. Moles cancel out, and we are left with an overall answer of negative 6,245 kilojoules. So hopefully that one was pretty easy. Whenever you're ready, you can flip your sheet over, and we will move on to our next problem. So our next problem is looking at enthalpy of formation. So we have enthalpy of combustion, which is the breaking apart of something. Now we're going to look at the enthalpy of formation, which is forming something. So standard enthalpy of formation. Notice the enthalpy of combustion had a C down here. Enthalpy of formation has an F. So C is down here for combustion, F for formation. So we're going to go ahead and look at this very first problem here. See how we can do. Okay, so enthalpy of formation is going to be the enthalpy change for a reaction in which 1 mole of a pure substance is formed from its free elements at stable conditions. Oops, sorry, is formed. Remember our standard state conditions, or our stable conditions, are at 25 degrees Celsius and 1 atm, or 101.3, or 760 millimeters of mercury. Another way that we talk about this is we call it heat of formation. So down here we have the standard enthalpy of formation of CO2 is negative 393.5 kilojoules per mole. This is the enthalpy change for an exothermic reaction. So I've got carbon solid plus oxygen gas becomes CO2 gas. Our enthalpy of formation is equal to our enthalpy, which is negative 393.5 kilojoules. Now, if instead we're looking at the formation, so we're looking at the formation of CO2 here, instead we're looking at the formation of NO2, we want to note that this is based off of 1 mole of substance. So we've got a mole of NO2 down here. Our enthalpy of formation of NO2 is a positive 33.2 kilojoules. The reason that we have a mole over here is because it's based off of, formation is always based off of 1 mole of a substance, which is why we have a half over here. Because our true balance equation would not have a half, but since we're looking at just forming 1 mole of this, we're going to have a half of N2 over here. Okay, so our example problem, ozone, O3, forms from oxygen by an endothermic process. UV radiation is the source of energy that drives this reaction in the upper atmosphere. Assuming that both the reactants and products of the reaction are in their standard states, determine the standard enthalpy of formation, delta HF of ozone from the following information. So this F I actually accidentally double typed. It shouldn't have been here. This one should. So you might want to just scribble that little guy out. Okay, so we have our overall equation. This is known as a thermochemical equation. So we've got our thermochemical equation, which gives us our enthalpy, or heat, of the reaction. So we have our enthalpy, or heat, of the reaction. Now, formation of ozone, we're looking at ozone, is in regards to 1 mole of the substance. And as you look here, our delta H is for 2 moles of ozone. So we need to convert this into 1 mole of ozone. So what we're going to do is we're going to take our enthalpy, which is our 286 kilojoules, and we're going to divide it by the 2 moles of O3. And when we do that, we end up getting a positive 143 kilojoules per mole being our enthalpy of formation of ozone. Remember, it's for 1 mole. That's why we have to convert it to 1 by dividing by the coefficient of 2. Okay. So if you wanted to write down an equation for how you would do this, you would take the enthalpy, so the delta H, and you're going to divide that delta H by the coefficient, and that will give you your enthalpy of formation. Okay. So let's look at a practice problem here. This practice problem says that hydrogen gas, H2, reacts explosively with gaseous chlorine, Cl2, to form hydrogen chloride, HCl. What is the enthalpy change for the reaction of 1 mole of H2 with 1 mole of Cl2 if both of the reactants and products are at the standard state? The standard enthalpy of formation of HCl is negative 92.3 kilojoules per mole. So this one's a little bit different. This one we have to figure out what our equation is. So it tells you hydrogen gas reacts with chlorine gas to make HCl. Now I have H2 and Cl2. I only have one of each over here, so I am going to need a coefficient of 2 in front of this to give me my balanced equation. It wants to know what is our enthalpy of formation. We don't know that, but we do know, we don't know our enthalpy of the reaction. We do know our enthalpy of formation. So we don't know our enthalpy of the reaction. However, we know our enthalpy of formation of HCl is negative 92.3 kilojoules per mole. So to figure out our enthalpy of our overall reaction, what you're going to do is you're going to take our number of moles, and we're going to take that and we're going to multiply it times our enthalpy of our formation. So I'm going to go ahead and pause the video, give you guys a moment to try that, and then we'll check back in. Okay, so now that you've had a chance to try this, we're going to take our moles of HCl, which is 2, and we're going to multiply times our enthalpy of formation, which is negative 92.3 kilojoules per mole. This ends up giving us our enthalpy of our reaction being negative 184.6 kilojoules. So we would add that up here to write our thermochemical equation. Now, writing reactions for the enthalpy of formation, remember we're forming 1 mole of a substance. So for example, the formation of C2H5OH is going to be carbon plus 3 hydrogens plus half an oxygen, making 1 C2H5OH. Other things that you might want to know are delta H of formation and combustion. The units are always in kilojoules per mole. And if we were to figure out our equation, which I have over here for you, but if we wanted to figure out the delta H of our reaction, that would be our enthalpy of formation times our number of moles. All right, and that is it for our enthalpy of combustion and enthalpy of formation.